says. All right. All right, welcome everybody. We'll just let a couple more people sign up here before we get started. Welcome to the study session. Maybe while you're getting settled in, maybe just give us a little shout out on the chat. Let us know where you're from. And we'll just give a couple more minutes for some more participants to come in here. So it's just 8 o'clock now, so. Good morning. Oh, I think I remember you from the last week's session on mechanics problems, I think.
Yeah, I was wondering if we get any repeat customers.
Looks like it. Still only 5. All right. Well, I guess we'll get started. Numbers, not a lot, but maybe a couple more will join in over the next couple of minutes. So welcome to our study session on topic E, atomic and nuclear physics. I'm, of course, Jim Irvin. I teach on the west coast of Canada in beautiful Victoria, British Columbia. Really happy to be joining everybody this morning to run this atomic and nuclear physics section. Running the chat for me is Gordon Hirons, who is, of course, the Revision Village physics head. So if you have any questions during it, please fire them into the Q&A, not the chat. And Gordon will be more than happy to answer those questions as we move along. Today's schedule is a little ambitious. We're going to be looking at some atomic structure, making sure we understand some of the key definitions, looking at some spectra, and ending with the Bohr model, focusing on the hydrogen atom. And then we're going to look at some binding energy and the energy-mass relationship, and look at some of the important nuclear reactions. And then we're going to switch to a higher level portion and go over some of the quantum physics material. So that's our plan for today. Kind of 2/3 standard level, 1/3 higher level is sort of, I think, how it's going to turn out. We'll see how our timing goes. We'll take a little break towards the middle for some survey, and we'll keep plugging along. Gordon has posted a link to the slides in the chat. So if you want the slides, then help yourself to the slides from the chat. And we'll see. Topic E, atomic structure, is a pretty big topic in the IB curriculum, and lots of interesting physics happening in here. So, but some new definitions that we have to be comfortable with. So one of the new definitions is a new definition of mass. So the unified mass unit. It's very typical in physics when you're dealing with physics at a different scale to switch to a different mass unit. So for example, when you go up to astrophysics, there's different units of length that deal with that scale of length at the astrophysics level. Here at the nuclear physics level, we're going to redefine the unit of mass to give us a new unit of mass that makes a little more sense with the scale and makes our calculations a little bit friendlier. So, and it's called the unified mass unit. In chemistry, they call it the atomic mass unit, but it's the unified mass unit. It's actually called the Dalton, but nobody calls it that. And it's defined as 1/12 the mass of carbon-12. So that's our unified mass unit. It's 1/12 the mass of a carbon-12 atom. And so that's a popular definition that pops up in a lot of sort of multiple choice questions, whatnot. What's the definition of the unified mass unit? It's just 1/12 the mass of a carbon-12 atom. A carbon-12 atom, of course, is 6 protons, 6 neutrons. So it's a nice balanced nucleus. and 1/12 of that we define as the unified mass unit. In the data booklet, you will see the conversion between the unified mass unit and the kilogram. So one unified mass unit is 1.661 times 10 to the negative 27 kilograms. You'll also see it in terms of this kind of unique looking unit here, the mega electron volt per c squared. And I'm going to come back to this mega electron volt per c squared a little later in our lecture, so you can see where this comes from. But this is indeed another unit of mass, the mega electron volt per c squared. And it does look a little weird, but I'll derive where that comes from. And this actually becomes a really important number for atomic and nuclear physics, this 931.5 mega electron volts per c squared. So this is an important one to key in on in the data booklet. Now, if we convert the mass of the protons and the neutrons and the electrons into this unified mass unit, we can see that the proton has a mass of 1.007276 unified mass units, and the neutron has a slightly larger mass, 1.08665 unified mass units, and the electron has 0.000549 unified mass units. And these are also all given in the data booklet. So these are important masses to keep track of as we work through the unit. So they're all given in the data booklet. The mass of the proton is given in all of the units, same with the neutron and same with the electron. So it's good to keep track of those. So we've got this new mass unit, the unified mass unit, lowercase u. Just out of, for interest's sake, if you look on the periodic table at the atomic masses, they're given in this unit of the unified mass unit. So that's one new unit that we're going to play around with. When it comes to doing questions, it's important to be able to do your work in either unit, the kilogram or the unified mass unit, and to understand how to switch between the units. Sometimes IB questions will ask for a specific unit in the answer. So it'll say, what is the energy in joules, or what is the mass in kilograms? And so it's important to be able to do your unit conversions. Another unit that we're going to start to use is the electron volt. So the electron volt is a unit of energy, and a lot of our atomic and nuclear energies will be given in terms of an electron volt. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Now, this conversion isn't directly given in the data booklet that I know of. I haven't seen it yet, but important, this 1.6 times 10 to the negative 19, this is the charge on the electron. This is the elementary charge, 1.6 times 10 to the negative 19 coulombs. And so that's one way that you can remember this conversion. The definition of the electron volt is this is the work done to move an electron through a potential difference of 1 volt. So it's the work done to move an electron through a potential difference of 1 volt. And if you remember from topic D, fields, work is equal to Q times delta V. And here Q is E, the elementary charge, and delta V is 1. And so that's where you see this conversion factor of 1 electron volt is 1.6 times 10 to the negative 19 joules. So it's a very common energy unit to use in atomic and nuclear physics is the electron volt. And sometimes we even add a mega in front. And remember, mega is 10 to the 6. And so you'll see that in this unique unit of mass down here, the mega electron volt. So often we'll put a mega in front, and it's 10 to the 6 electron volts. Our last idea, definition that we have to get very comfortable with is the idea of the photon. And this ties into a lot of our work with quantum physics. The photon is a particle of light. And I know that in topic C, we do a lot of work with waves, and light is a wave and behaves like a wave, but light can also behave as if it's a particle. And the photon is the particle of light. I like to tell my classes, imagine it's a very, very small, maybe one wavelength of that light traveling through. So instead of having a light bulb that's emitting these long, continuous waves of electromagnetic radiation, think of it as emitting all these tiny little photons of like single wavelengths of light in all directions. So, so that's what I like to think of as the photon. But the photon is the particle equivalent of light. And we're going to be doing all of our work in this unit considering light as a stream of photons. And the energy of a photon, and you can see this formula is in the data booklet, the energy of a photon of light is equal to Planck's constant times the frequency of the light. So if we treat light as a particle, then we can treat it as a photon, and the energy of a photon is equal to hf. H is Planck's constant, which is in the data booklet, and Planck's constant has the value of 6.63 times 10 to the negative 34 joule seconds. And Planck's constant pops up a lot in the atomic and nuclear physics unit. Now, there's another version of this formula that's not given in the data booklet that's important to use, especially in the atomic and nuclear, especially when we talk about Bohr model, but it pops up a lot. And it comes up when you combine these two formulas together. E equals hf is the energy of a photon, where f is the frequency of the photon, frequency of the wave. And this formula, V equals F lambda, this is the formula for the speed of a wave. It's called the universal wave equation. V is the speed of the wave, F is the frequency of the wave, and of course, lambda is the wavelength of the wave. And since photons are light, if we think about V equals F lambda, the speed of light is given by C, 3 times 10 to the 8 meters per second. So if we replace this symbol v, which is just an arbitrary speed of any wave, with the specific speed of light, c, we can say that the speed of light, c, is equal to the frequency times the wavelength. If we rearrange this equation for the wave or for the frequency, we can see the frequency is the speed of light divided by the wavelength. And if we put this formula in our energy of the photon formula, then we get a formula that tells us the relationship between the energy of the photon and the wavelength of the photon. And this is the more commonly used energy formula for the photon, because we often want to talk about the wavelength of the photon, because of course our electromagnetic spectrum is organized in terms of wavelengths, not frequencies. So we need to be more comfortable thinking about the wavelength of the light, the wavelength of the photon, so that we can identify what area of the electromagnetic spectrum the photons are coming from. And so this formula, this specific version of the formula, is not in the data booklet. You're left to sort of dig it out from combining these other two formulas. Okay. But what is in the data booklet are these two HC conversions here. And this little piece here is really handy. It's underneath the table of the metric prefixes, and it is under this little section called useful conversions or something like that. And here you see H times C, Planck's constant times the speed of light. And you'll notice that's the top of this equation for the energy of a photon in terms of its wavelength. And so this saves you some time in calculations. Instead of trying to calculate H times C, you're given H times C, and you're given it in both sets of units, joule meters and electron volt meters. So it's very handy to remember that. So if you're doing a calculation that involves this formula with the energy and the wavelength, you don't need to calculate HC. It's already given to you. So it saves you some time and some effort just to remember that those are in the data booklet, although this specific version of that energy formula at this point does not appear in the data booklet. So you have to dig that out a little bit. So those are our three kind of new definitions that we want to play around with. This new definition of mass, the unified mass unit, this definition of energy, the electron volt, and this idea of photon as the particle of light. Another thing that shows up a lot in this atomic structure section is these ideas of spectral lines and spectrums. And I just wanted to quickly take a minute and go over these spectrums because they're so critically important that I think it just warrants a little discussion of it. In the data booklet, you do see an electromagnetic spectrum. It doesn't look like this one. This one I got off Wiki Commons, but it does show you the breakdown of the different areas of the electromagnetic spectrum, and it does show you the breakdown of the visible light spectrum, and it's in order of wavelength. Now, it goes from short wavelength to long wavelength, which is kind of the reverse order that a lot of us meet the electromagnetic spectrum. And so it starts with gamma and it ends over here with radio, and it breaks down the different regions of the electromagnetic spectrum. So you are given the electromagnetic spectrum, so you don't have to try to memorize the electromagnetic spectrum. But what you should know about the electromagnetic spectrum is roughly the range of the visible light spectrum. 400 to around 800 nanometers is sort of the rough edges of the visible light spectrum. That's always great to tuck in the back of your mind, because often the IB will ask questions of, you'll find the wavelength of a photon, and then it'll ask where in the electromagnetic spectrum is this wave. And so if you know that the visible is between 4 and 8, then you can identify, well, is it in the visible? Whereabouts is it in the visible? Is it infrared or is it ultraviolet? So you can sort of identify what areas of the electromagnetic spectrum that photon is from. Now, in terms of electromagnetic spectrums, there's two types of atomic spectra that we deal with. And one is called an emission spectrum. In an emission spectrum, the light that is creating the spectrum is actually from the source of the light. So we have a light source that's passed through some sort of spectrometer or a prism to break it up into the individual wavelengths. So, and then we see the individual wavelengths of that light source broken into the spectrum. If there are no gaps in the spectrum, if it's a nice rainbow, then this is known as a continuous spectrum. So light sources like the sun or light bulbs, they produce a continuous spectrum of light. So every wavelength of light is present in the spectrum. However, what we're going to see from the Bohr model is some materials produce a very distinct set of colored lines. Right? And so if we use a gas discharge tube, like the Bohr model, like Bohr was doing, a gas discharge tube full of a pure substance, neon, xenon, hydrogen gas, and you put high energy voltage or high voltage across the ends, it will emit light. And if that light gets put through a spectrometer, then it emits these very specific color bands. Still an emission spectrum because it's made from light that's being emitted from the source, but it's no longer a continuous spectrum. This is what we call a discrete spectrum because it's showing very specific wavelengths of light. But these are known as emission spectrums because the light is coming from a light source to create the electromagnetic spectrum, whether it's a continuous or a discrete spectrum. On the other hand, we have what's called an absorption spectrum. And in an absorption spectrum, we start with a white source of light, a continuous light source. And that white source of light is passed through our sample. So it's passed through a gas or a liquid, has to be able to get through the sample without diffusing or reflecting off, because on the other side, we're going to collect the light that comes through, and we're going to see that there's gaps in that continuous spectrum. This is called an absorption spectrum because it's showing that some wavelengths of light have been absorbed. So wavelengths have been absorbed. So the spectrum is not actually being created by the white light. It's being created by the cloud of the sample absorbing specific wavelengths of light, and it's leaving gaps in the spectrum, in that continuous spectrum. This is known as an absorption spectrum. They show the exact same thing. You'll notice that these two spectral patterns that I have here show the same wavelength lines. Here we have a red, a green, and a blue shown from the emission spectrum. That's the light that's coming from this gas discharge tube, split into its individual wavelengths. Here we have a red, a green, and a blue that are missing from the continuous spectrum. Those have been absorbed by this cloud of gas, and they're now missing from the continuous spectrum. So both tell the same information. They're just produced through different means. One is caused when the gas is excited and release light. One is caused when the gas absorbs light. And so it's an absorption versus emission spectrum. And they do come back into our story in a little bit. So just to keep those in mind as we move forward. Right? So we've got our new units for mass and energy. We've got the photon as a particle of light, and we've got these atomic spectrums, the emission and absorption spectrum to think about. From there, we can start to talk about the Bohr model. The Bohr model is an atomic model that kind of puts all the pieces of the puzzle together. If you think about the history of atomic structure, J.J. Thomson discovered the electron using the cathode ray tube, and he had that famously named atomic model known as the plum pudding model, in which he envisioned the atom as being a dough of positive material, positively charged material, with negatively charged electrons embedded in it. So that was sort of the start of our atomic model theory. And then Rutherford discovered the nucleus, found that it was a positively charged, very dense, very small region of the atom. And then Bohr, using the gas discharge tubes, came up with the theory about the behavior of the electron. Put the nucleus in the center of the atom, very small, positively charged, very dense. And according to the Bohr model, the electron is orbiting this nucleus at very specific energy levels. So the Bohr model has the electron orbiting the nucleus at very specific energy levels. So it can't just be anywhere. It only exists in very specific orbits around the nucleus. And in the data booklet, for the higher level students, it's under the higher level section, you'll see this relationship that actually calculates the energy level of the electron orbitals in the Bohr model. But this is only for hydrogen. So just be aware, this is only for hydrogen. But you should be able to sort of notice when things are hydrogen and when they're not hydrogen. The question will often state for a hydrogen atom, and then you know you're dealing with hydrogen. But sometimes it won't state, but you'll be able to tell by looking at the energy levels, whether you're hydrogen or not. And hydrogen has a very characteristic electromagnetic spectrum. And so we should be comfortable with some of the hydrogen lines that occur in the electromagnetic spectrum. Hydrogen is a very, very important atomic electron orbital arrangement for us to be comfortable with. Right? So this relationship will allow us to calculate the energy levels of the electron in the hydrogen atom. So for example, the very first energy level, we would say n equal to 1. We use the n value to identify the energy levels. So the first energy level of the electron in the hydrogen atom, we would put 1 into this relationship, and we'd see this is at minus 13.6 electron volts. So the first energy level has the value of minus 13.6 electron volts. The energy is negative because this is what we refer to as an energy well. There's an attractive force acting between the electron and the proton, so they're stuck. They're stuck together. So this mathematically models as a negative potential energy. So the energy of the electron at the first energy level is negative 13.6 electron volts. If we put in n equal to 2, we can calculate the energy level of the second orbital. It's going to be negative 3.4 electron volts. And n equal to 3, we can calculate that, minus 13.6 divided by 9. And we'll see that this is minus 1.5 electron volts. So you can see these energies are getting bigger. Even though they're negative, negative 1.5 is bigger than negative 13.6. So as we move away from the nucleus, our energy levels are getting higher energies. So the electron is able to move between these energy levels. So in the Bohr model, the electron is able to move. It can jump between any two energy levels, and it does so by absorbing or emitting energy. And that energy has to be in the form of a photon of light. So the electron, and we often use the term jumps or falls. So the electron can move between energy levels by absorbing or emitting a photon. So this is our other idea of the Bohr theory of the model. So it can jump between these energy levels by absorbing or emitting a photon of energy. So you can see I've got up here a little photon. This photon is going to come in. If the electron were to absorb that photon, then we would see that electron would jump to a higher energy level. So maybe it absorbs it, and maybe it pops up to the n equal to 2 because it absorbs that photon of energy. Or maybe there's an electron at n equal to 3, and it emits a photon of energy and falls to n equal to 1. So the electron can jump back and forth between these energy levels by absorbing or emitting a photon of energy. So this is an emission. And this would be an absorption. Absorption takes you up an energy level, whereas emission will drop you energy levels. And they can jump between any two energy levels. It doesn't always have to be n equal to 1. They can go between 2 and 3, 3 and 1, 5 and 3, whatever. Because, of course, these energy levels continue spreading out until eventually you have an infinite level of energies. So the trick here is that the photon that gets absorbed or emitted has to be of a very specific magnitude of energy. So the photon that gets absorbed or emitted has to match the difference in energy between the two energy levels. So the photon energy must match the energy difference between the two energy levels. If it doesn't, it's just going to pass through the atom and it's not going to interact with the electrons. It has to be the exact value between the two energy levels for the electron to interact with it. And I'll show some examples of this in the next slide. So in my example here, I have a photon coming in and getting absorbed, and my electron jumps from n equal to 1 to n equal to 2. This photon has to have exactly this difference in energy for it to occur. If it doesn't, it's just going to pass through the atom and keep going. Same thing with this emission of the photon. The photon that gets emitted has the exact energy of the difference between energy 3 and energy 1. And so that difference in energy would relate to the wavelength of this photon that gets emitted. Has to be those exact values. And this is known as quantized energy because there are exact specific values for the energy levels and for the photons and the wavelengths of the photons that are being absorbed and emitted. So now, because these photons are specific energies and specific wavelengths, that results in our electromagnetic spectrums, our unique spectral lines for the different elements. So as we look at some of these spectral lines, the fact that they have a very specific wavelength relates to a very specific jump or falling between these energy levels. So that results in our spectrums. So when a photon gets absorbed and the electron jumps from a lower to a higher energy level, then this results in the absorption spectrum, because that photon is now missing from that continuous spectrum of white light. So if you imagine all of these photons coming through this atom, the one photon that has the right specific wavelength gets absorbed. So now that continuous spectrum has a gap in it where that wavelength got absorbed. And that relates to the absorption spectrum for this element. Similarly, when an electron falls from a high energy to a low, it emits a photon, and that relates to the emission spectrum. So you'll see the emission spectrum occurs when the electron moves from high to low, and the absorption spectrum when the electron moves from a low energy to a high energy. So that accounts for our two different types of spectral lines as a result. So if you have any questions, please feel free to put them in the Q&A, and Gordon will be happy to answer them for you as we go through. There's a lot of material that we're kind of moving through pretty quickly. So now, often, more commonly, the energy levels are drawn as a series of horizontal lines and not drawn as concentric circles. Concentric circles are good for visualizing what the electron is doing, but drawing them as horizontal lines is a better way to do it. And each of the horizontal lines relates to the energy level. So our first line at the bottom would be n equal to 1, the first energy level. So this inner orbit. The next one will be n equal to 2, and then n equal to 3, n equal to 4, n equal to 5, and so on and so forth until infinity. You'll notice that as these lines get bigger, as the energy gets larger, these lines start to get closer and closer together. So the energy levels start to get closer and closer and closer together until eventually they're so densely packed that you can escape the electron can escape the nucleus. It can escape the atom, and in that case, you formed an ion. So, and we'll talk about that in a little bit. And of course, we've got our relationship that allows us to calculate what the energy level is. And so, as we showed previously, our first energy level is minus 13.6 electron volts. Our second is minus 3.4 electron volts. Our third is minus 1.5 electron volts. I've rounded these to 1 decibel, but you can go more accurate. This is minus 0.85. I'll put a second decimal here. And the last one is minus 0.54. And so you can see that the difference between these energies is getting smaller and smaller and smaller. So even between 4 and 5, that's a difference of only about 0.3 electron volts. Whereas to go between 1 and 2, that's a difference of just over 10 electron volts. So a much bigger difference between 1 and 2 and 4 and 5. And if we were to continue n equal to 6, n equal to 7, n equal to 8, these lines would get closer and closer and closer together. So one of the benefits of drawing the energy levels as these horizontal lines is we can show whether the electron's moving up or down pretty easily. So for example, if I had an electron that moved, say, from 3 to 2, I could draw it moving down like that. I could put an arrow on it showing that it's moved from 3 to 2. This would be an electron moving from a higher to a lower energy. So this would result in an emission of a photon. If I wanted to draw it moving up, I could draw it with an arrow pointing up 2 to 3. There's the same jump. It would involve the same wavelength of a photon, but in this case, it's being absorbed. So this is a photon being absorbed, and that electron has moved from 2 to 3. And in my first case, this is an electron being, or a photon being emitted, and the electron falling from 3 to 2. And so the upward arrow would result in the absorption spectrum, and the downward arrow would result in the emission spectrum. Now, of course, this would relate to a very specific wavelength of the photon. So we can calculate what that wavelength would be. So if we find the wavelength, we could say that the energy of the wavelength has to equal the difference in energy between the energy levels. So let's consider emission. So let's think about emission. And let's say n equal to 3 to n equal to 2. So let's say that our electron's going to move from 3 to 2, losing energy and emitting a photon as a result. So we could say that the change in energy that the electron is going to experience is final minus initial. Final is 2, and initial is 3, E2 minus E3. And so I can sub in my energy level values. So the energy of the second orbital is minus 3.4, and the energy of the third is minus 1.5. So I could say this is going to be equal to minus 3.4 electron volts minus 1.5 electron volts. Now I have to be really careful with my minus signs because these energy levels are negative potential energies. And so I have to put them in as minuses. And if you do that, things will be all nice for you. And you'll see that this works out to minus 1.88 electron volts. So that's the energy that's released. This minus sign, because I'm dealing with a change in energy, this minus sign tells me that the energy is being released from the electron because it's lost this amount of energy. So that would be the energy that the photon would have. So this is the energy of the photon that's being released in that electron movement. So now I can go to my formula for the energy of a photon, hc, and I'm going to use the version hc over lambda that we showed earlier. And then I can use that hc value that's on the data booklet, so I can save myself a little bit of time. And I can go, this is 1.24 times 10 to the negative 6 over the wavelength. And I've got the energy, it's 1.88. And so I can solve this for the wavelength. This gives me a wavelength of 656 nanometers. Now I am skipping a couple steps because this wavelength will be in meters. And so I've switched it into nanometers just for the sake of pointing it out on where it is on the electromagnetic spectrum. And 656, that is red. So this is the characteristic red line for hydrogen, the 656 nanometer red line, which is a really important line in terms of atomic and nuclear physics, the 656 nanometer red line. If we were to continue doing these calculations for other jumps, we would see that the jump between 4 and 2 results in another visible light line. It results in like a greenish kind of line. There's also 5 to 2, which results in sort of a purplish blue line. And there is another one, 6 to 2. So you'll see that the hydrogen spectrum actually contains 4 visible lines. And if you end at the second orbital, this results in your visible light spectrum. So any electron movement that begins or ends at n equal to 2, the second energy level, will result in the visible spectrum for the element. If you go down to n equal to 1, now these are much longer jumps, and so the energy will be a lot bigger. And remember, the relationship between energy and wavelength is inversely proportional. So the bigger the energy, the shorter the wavelength. And so what's shorter than visible? These would result in an ultraviolet spectrum. So you'll get spectral lines, unique spectral lines, but now they're in the ultraviolet if you're down here at the n equal to 1 energy level. N equal to 3, these would result in your infrared spectrum. So ending or starting at n equal to 3 will result in your infrared. So it's important to remember this relationship between energy and wavelength and the line, how big this jump is. The longer the jump, the bigger the energy. The bigger the energy, the shorter the wavelength. So the shorter the jump, the smaller the energy. The smaller the energy, the longer the wavelength. So it's important to try to remember that, especially when we start doing like multiple choice questions and things like that. So if you have a long line, so if you have a big jump, that means big energy, and that means short wavelength. Right? And then the reverse is also true. Right? So if you have a short jump, small energy, long wavelength. Right? So this is very popular in the multiple choice for atomic and nuclear, playing around with these energy levels and jumping around. Right? And do be careful, because I have seen the odd question where the energy levels have the same spacing between them. And if the energy levels have the same spacing between them, then it's obviously not hydrogen. It's a different theoretical setup. But if they have the same spacing, then they're going to release the same wavelength of the photon. And so and I have seen the odd multiple choice where the IB has tried to set this kind of question up. And if you have sort of a theoretical energy arrangement where they're all like maybe 1, 1.5, and 2. So if they're all, I should have those backwards. So if we say that we're at -2 and then minus 1.5, and maybe this is -1 electron volts, then these are all evenly spaced energy levels. And so an electron that, say, falls from 2 to 1 or 3 to 2, they're going to release the same wavelength of photon because that difference in energy is the same. It's 0.5 electron volts. And so just be aware of that. Keep an eye out for that in the multiple choice a little bit. Now, if you want to completely remove an electron from the atom to create an ion, then you have to give it, in this case for hydrogen, you'd have to give it 13.6 electron volts. So if you want to remove an electron, then its final energy will be 0. And so to ionize, the energy needs 13.6 electron volts. And we can go on to calculate what wavelength of a photon this would require. And it's going to be in the ultraviolet. So a very specific wavelength of ultraviolet will interact with this electron and actually cause it to leave the atom entirely. And then you have an ion. So this is known as the ionization energy for this element. So that's the Bohr model in general, playing around with the Bohr model and the electron orbits and jumping up and down. I wish I could spend more time on it, but of course, we've got a lot to cover today, and we're already halfway through our session. So I'm going to have to start moving a little faster here. So another thing that we want to talk about is the relationship between energy and mass. And you'll see in the data booklet, E equals mc squared, this wonderfully famous equation relating energy and mass. And this is where a lot of my students kind of struggle a little bit, because they're really they've really embraced that classical mechanics version of mass, this Newtonian version of mass as inertia and resistance to acceleration. And I always say to them, hey, you got to let that go. You got to let that go. We have to come up with a new idea of mass. And mass is just it's just related to energy, right? The idea that E equals mc squared is telling you that it's the energy an object contains as a result of its mass. So this E equals mc squared formula is just a relationship between energy and mass. And the idea that we want to try to embrace is that energy can convert to mass and mass can convert to energy. Right? So energy can convert to mass and mass can convert back to energy. And that energy is in the form of electromagnetic radiation for the most part. So we can switch back and forth between energy and mass. And that E equals mc squared, that's the relationship that allows us to convert back and forth between energy and mass. And of course, c is the speed of light squared. Now, previously, we talked about that unique unit, the mega electron volt per c squared. Well, that comes from this relationship. So if I solve this for mass, so I can say mass is energy over c squared. So you can see now I have a definition for mass that's in terms of a unit of energy divided by c squared. So if you think about that unit, the mega electron volt per c squared, that's a unit of energy divided by a unit c squared. And so this is where this unit of mass comes from. It comes from applying this E equals mc squared and just rearranging things for a definition of mass. Now, why that is so handy is that if you do the conversion for one unified mass unit, you can see that this works out to 931.5 mega electron volts per c squared. And so this becomes a really friendly little conversion factor to convert energy directly from unified mass units and calculate how much energy is related. So if your mass is in unified mass units, then you just end up having to times it by 931.5, and you get the associated amount of energy related. So basically, we would do this calculation. We would say the energy is the unified mass unit, and then I can convert that into mega electron volts per c squared. So this little calculation converts my unified mass unit into this other unit of mega electron volts per c squared. And then in my formula, I times it by c squared. And then what happens mathematically is those c squareds cancel out. And so long story short, a really easy way to convert your energy from unified mass units into energy units is just to times it by 931.5. And so it becomes a really friendly, quick way to calculate energy from mass if your mass is in unified mass units. If your mass is in kilograms, then you're going to have to get it, you're going to calculate your energy in joules. You times it by c squared, and you get your energy in joules. So now if we talk about this idea of E equals mc squared and start to look at some atomic nuclei. So if we consider the helium nucleus, 2 protons, 2 neutrons, if we were to add the total mass of the nucleons, remember nucleon is a particle that's in the nucleus. So protons and neutrons are nucleons. So if I take this helium nucleus and I add the total mass of the nucleons, remember a proton has a mass of 1.007276, and a neutron has a mass of 1.008665. So if I add up the mass of the nucleons, I see that this is 4.0319 unified mass units. Great. So there's my mass of 2 protons and 2 neutrons. But if you actually arrive at the experimental mass of the nucleus of helium, then you notice something kind of strange. And that is that it's a little bit lower, 4.0015 unified mass units. The mass of the nucleus is not the same as the mass of the nucleons. It's a little bit smaller. And if we did this for any isotope that's available in the atomic and nuclear world, you would see that the same thing would apply. The mass of the nucleons is always a little bigger than the mass of the nucleus. And this difference in mass has the name of the mass defect. So the mass defect, which is given the symbol of a lowercase gamma, this is the difference in mass between the nucleons and the nucleus. So this would be the nucleons minus the nucleus. And we're talking mass. The mass of the nucleons minus the nucleus. So for my helium nucleus, this mass defect works out to 0.0304 unified mass units. So that's the difference in mass between the nucleons and the nucleus. And what's happened in forming this nucleus from its base nucleons is we put the nucleons together, and then to make it stable, a little bit of energy gets released. And that energy comes from this very small amount of mass. So this mass defect, it relates the amount of mass that gets converted to energy and released when the nucleus forms. So we can calculate the amount of energy that gets released by just timesing this mass by our new value of 931.5 mega electron volt per c squared. So the energy released, E, is equal to 0.0304 times 931.5, which gives me 28.32 mega electron volts. That's the energy that gets released when that helium nucleus forms from its nucleons, protons and neutrons. This energy is what we refer to as the binding energy. So the binding energy is the energy released when a nucleus forms from its base nucleons. There is another definition of binding energy, which is also accepted, and that's the energy needed to completely take apart a nucleus. So if 28.32 mega electron volts is the energy that's released when the helium nucleus forms, 28.32 mega electron volts is the energy I would need to put back in to separate the nucleus into those 4 nucleons again. So either version of this definition is acceptable. So there's my binding energy for nuclear, for helium. Now, if I went on and calculated other binding energies, I could say that. So my helium binding energy was 28.32 mega electron volts. And if I just pick a couple other isotopes at random, like let's say I do barium 11, then it has a binding energy of 76.2 mega electron volts. And if I pick, say, iron 56, this has a binding energy of 429.8 mega electron volts. And if I choose, say, uranium 236, get a really big nucleus in here, this has a binding energy of 1,790 mega electron volts. And so we can see that as the nucleus gets bigger, the binding energy gets bigger, which makes sense because you'd need more energy to assemble or disassemble these larger collections of nucleons. But then the question is, are these nuclei all the same level of stability? How can we compare the nuclear stability of these nucleus? How likely are they to interact through nuclear reactions such as fission, fusion, the whole host of other nuclear reactions that occur, right? How do we compare the actual nuclear stability? Because the binding energy, it makes sense that the larger a binding energy is, the more energy it takes to take it apart. So there is an inherent stability there, you would think. However, we also have this idea that the bigger nuclei will require larger binding energies. So the trick is to calculate the binding energy per nucleon. And this will give us an idea of how much energy is required for each nucleon, and then we can directly compare the stability. So if I make those calculations for my isotopes, the binding energy per nucleon of helium works out to 7.08, and these are all in units of mega electron volts per nucleon. For the boron, I think I said barium before, but for the boron, this is 6.92, so slightly smaller, a little less stable. For the iron, this is 8.8, so more stable, larger binding energy. And for the uranium-236, 7.58. So we can compare the nuclear stability by looking at this binding energy per nucleon, taking the binding energy and dividing it by the number of nucleons in the nucleus. If we then go on and calculate every isotope's binding energy per nucleon and build a binding energy per nucleon graph, we can see an interesting trend. So if I put my 4 nuclei on this graph, you can see I've got, let's see, if I scale this up to about 9, because you can see iron goes to about 8.8. So I'll scale my graph up to 9. I can say, okay, well, helium is 4, and it's going to be here at around 7. And then here's boron, just a little bit to the right at 11, and it's going to be a little lower. And then I've got iron, which is 56. So it's going to be a little further to right, and it's going to be higher up here around 9. And then way over here, I've got my uranium, and it's at around 7.6. So it's going to be around here. And if you continue to do this, you get the binding energy per nucleon curve, which looks roughly like that. And you can see that iron 56 is actually at the top of the curve. And this binding energy per nucleon curve shows us the relative stability of all the nucleus. The higher the binding energy per nucleon, the more stable the nucleus is, the more unlikely a nuclear reaction will be. It also splits all of the atomic nuclei into sort of 2 halves. On the right, we have nuclei that are too big, and so they are trying to get smaller. And so these are all going to participate in the nuclear reaction that makes nuclei smaller. They're fission fuel. So a fission is a nuclear reaction where one large nucleus splits into 2 smaller nucleus and some neutrons are released. And so by doing that, the products of fission are going to climb this binding energy per nucleon curve, and then they're going to become more stable. On the other side, these nucleons or nuclei are too small. They're trying to fuse to increase their binding energy per nucleon. And so fusion is the nuclear reaction where 2 small nuclei stick together, form a larger nuclei. And so they're going to try to climb the curve this way to become more stable. Iron 56 is at the peak of the curve. Just beside it is nickel 62. These are the top most stable nuclei. They do not participate in either fission or fusion because they have the highest binding energy per nucleons at around 8.8 mega electron volts. So by looking at this binding energy per nucleon graph, we can then track the nuclear stability and see what nuclear reactions are likely to happen. Right? Now I see it's almost 9 o'clock, so I do want to make sure I have time for the higher level material, but I just really want to quickly talk about these reactions. And I'll just demonstrate one of them as opposed to doing all 3. So for example, if we look at a fission reaction, and there are a whole host of nuclear reactions, but if we look at a fission reaction where a large nucleus splits into multiple smaller and releases neutrons. So an example of a fission reaction is uranium-236 will split into an isotope of barium, barium-144, and an isotope of krypton, krypton-89, and 3 neutrons are produced in that fission reaction. So here we are for the fission reaction. Now, if I wanted to calculate the energy released in this reaction, I would just look at the change in mass from one side of the reaction to the other. We'll see that this has the larger mass, and all of this will have a slightly smaller mass. And so I could calculate the difference in mass. That's going to be the mass of the uranium minus the mass of the barium plus the krypton plus the 3 neutrons. Right? And so if I do that change in mass, this will give me what's known as the mass difference. And from there, I can calculate the energy released in this fission reaction. That energy will be carried by the neutrons in the form of kinetic energy. And another way to do it, and this will be my last point before I switch to the higher level material, another way to do it is to look at the binding energy of each side of the reaction. So if I look at the binding energy of uranium and the binding energy of barium plus krypton, I'll see that if I subtract those two, I'll get the energy released in the reaction. I don't need to consider the binding energy of the neutrons because neutrons are not nuclei, so they technically don't have a binding energy. And so I only need to worry about the binding energy of the uranium and the binding energy of the barium and the krypton, and I could subtract those, and then I'll get the binding energy, or I'll get the energy released in the reaction. And a common way to get those values is, of course, off the binding energy per nucleon graph. So I could take my uranium value, come over to the axis, find the binding energy per nucleon, times it by the number of nucleons. That will give me the binding energy of the uranium, and I can use that in my fission calculation. Right? I wish I had more time to go through that a little more fully, but we've only got about a half an hour left. So we're going to take a couple minutes here, if you have some time, to fill out this survey for us so that we can continue to modify our presentations to suit your needs and help you get ready for your exams a little bit more effectively. And then we're going to take a look at our quantum physics material, exploring the exciting world of wave-particle duality for the higher levels. And again, if anybody has any questions, feel free to put them in the Q&A. Gordon's more than happy to answer them. If any of the standard levels who aren't responsible for the higher level just want to ask Gordon some questions in the Q&A as well, you're welcome to. So give another minute or two for the survey. So it's 9:03. Maybe I'll go to about 9:05, and then we'll start up again. We'll also have some time at the end for more general Q&A if you want to ask about other topics, or if you want to ask about exam preparation in general. We can stay online for a while afterwards and answer some questions about that as well. Sorry, I had to rush through the reactions. All right, well, let's move forward now and take a look at some of this higher level quantum physics section here. A big part of the higher level quantum physics is just examining this idea of wave particle duality. And this is one of the core ideas behind quantum physics. It's this idea that waves and particles can share properties. And that's a really big idea in physics, because in physics, often there's a big wall between these two ideas. Things behave like waves, or things behave like particles. But quantum physics says no, waves can behave like particles, and particles can behave like waves. And so if you think about what are wave properties, what properties do waves have that particles don't have? And it's things like superposition. That's a wave particle. That's when two waves pass, or a wave behavior. That's when two waves pass through each other and their amplitudes add or subtract, constructive interference, destructive interference. That's a wave. That's a wave behavior. You wouldn't expect two bowling balls to pass through each other and create one giant bowling ball for a moment in time. And superposition leads to the idea of interference patterns, which of course is a large part of topic C, the wave behavior. And so interference patterns are a wave behavior that you wouldn't expect particles to exhibit. But quantum physics says no, particles can exhibit these wave-like behaviors. And in the data booklet, you'll see this little equation here. This is the de Broglie, I pronounce his name wrong, but it's the de Broglie. I don't think I'm saying the name right, but this is the de Broglie wavelength. This is the wavelength that a particle would exhibit in their wave-like behaviors. Because if you're going to behave like a wave, the wavelength is a really important aspect of that behavior. And so here is the wavelength that a particle would exhibit. H is Planck's constant, and P is the momentum of the particle. And so there's our wavelength of the matter wave, as it's often referred to. The wave-like behavior of the particle is linked through this wavelength formula. And the flip side of this are waves behaving like particles. So if you think about what a particle behavior is, these are things like collisions, exchanges of momentum, even just momentum itself, right? These kind of relationships that assume that you have mass, right? So momentum itself is a particle-like behavior. We don't, in our wave section, topic C, we don't talk about the momentum of waves, but because waves typically we consider to not have mass. And yet in quantum physics, the wave can have a momentum. And again, we can use this wavelength relationship and rearrange it and see that the momentum of a wave can be found by Planck's constant divided by the wavelength. And so this is a core idea of quantum physics, is this idea of wave-particle duality, that particles can behave like waves, and this is the wavelength they would have based on their momentum, and waves can behave like particles, and this is the momentum they would have based on their wavelength. So we're kind of mixing these two seemingly different branches of physics together into this world of quantum physics. And then there's a couple examples of these in action. And one of the big ones is the photoelectric effect, which is an example of waves behaving like particles. And the photoelectric effect is an effect that occurs when a photon of light is incident on a piece of metal and it causes electrons to be released by the metal. And it's a particle-like effect because we're dealing with a collision and an exchange of momentum occurring. In a wave-like effect, we might expect this photon of light to reflect off of the piece of metal, or maybe it'll be absorbed by the piece of metal, and maybe the piece of metal's electrons will change orbitals or those sorts of things. However, here we have a collision, and it actually causes an electron to be emitted from the metal, and off it goes. So this is our photoelectric effect, where waves are behaving like particles, where the photons cause electrons to be emitted from a metal. Now, the famous experiment that verified this involved a piece of metal inside a vacuum tube across from another terminal, and light shining on it, and then an ammeter attached that could measure current. And here we have a variable power supply that's put in the opposite direction. And initially, we could keep this turned off. And then we've got a voltmeter across as well to measure the voltage across the circuit here. So if the variable power source is off to start, then the light coming in will cause electrons to be emitted from the metal, and you'll see a current created in the ammeter, and you'll measure a potential difference across the two sides of the circuit. And if we start to turn up the variable power source, which is wired in the opposite direction, then this variable power source will cause the current to drop to zero. So this is a pretty famous experiment. And so what happens is this variable power source, which we call the stopping voltage, we adjust the stopping voltage until the current drops to zero in the circuit. Right? So when the current drops to zero in the circuit, then our stopping voltage is important. Because when the current drops to zero in the circuit, then the stopping voltage will be equal to the kinetic energy of the electrons. So when the current drops to zero, right, the stopping voltage, if we convert that into an energy, will be the kinetic energy of the electron. So we can calculate the kinetic energy of the electron being released. It's E, the charge on the electron, times the stopping voltage. Remember, this is our formula from topic D, fields. The work done in moving an electric charge through a potential difference is the charge times the potential difference. So we can use this to calculate the kinetic energy that the electron is being emitted from the piece of metal with. And then we've got a couple options. So we can either start to change the type of metal and see what happens, or we can change the frequency of the photon. So all of our photons are at the constant frequency. So if we change the frequency of the photon, then if we were to graph the frequency of the photon as a function of the kinetic energy of the electron, which again, remember, is E times the stopping voltage. So if we start to change this frequency of the incoming photons, then we start to see some interesting results. First of all, we see that for very low frequencies, electrons aren't emitted until eventually we hit a frequency where the electrons start to get emitted. So there seems to be a frequency, a minimum frequency required for electrons to be emitted from the material. And this frequency is called the critical frequency. The critical frequency, this is our minimum frequency of light to release an electron from the metal. And then as we increase the frequency of the light, we see that the kinetic energy of the electron starts to increase, which is kind of expected because as we increase the frequency, we're increasing the energy of the photon. And so we would think in a classical physics sense, increasing the energy coming in would increase the energy of the electron. And so we see that increasing the frequency increases the kinetic energy of the electron, and it's a linear relationship. So it's a linear relationship between the frequency of the photon and the kinetic energy of the electron being emitted. If we were to extrapolate this down and cross the y-axis, we would get what we call the work function. The work function capital Psi. The work function is the minimum energy needed to free the electron. Now, if we put together the linear relationship here and find the equation of the straight line, we'd see that the kinetic energy of the electron is equal to HF. H is the slope of this line, which is Planck's constant, minus the y-intercept, which is the work function. So we get this relationship that describes this linear relationship between the frequency of the photon of the light and the kinetic energy of the electron being emitted. And that formula is available in the data booklet. Also, this is the formula that allows us to calculate the kinetic energy of the electron, Q delta V, from topic D in the data booklet. So you can see this formula in the data booklet, E max equals HF minus psi. This is the equation of the straight line that comes from this experiment. F is the frequency of the light, the photon of the light. E max is the kinetic energy of the electron emitted from the metal, and psi is the work function. So the minimum energy required in the photon to release the electron. Now, if we change the type of metal, then we can see that the only thing that will change is the work function and the critical frequency. So if we change to a different type of metal, the slope remains the same. This is a different metal. The slope remains the same. We just get a new critical frequency and a new work function as a result. So changing the metal doesn't change the slope of the line. It just changes the energy required to free an electron from the material. Now, this is considered a quantum effect because there are some surprises here. The surprises are that the intensity of the light doesn't change the kinetic energy of the electron being emitted. So if we change the intensity of the light, which means we can change the intensity two ways. We can make the light source brighter, more photons per second arriving if it's brighter. That doesn't change the kinetic energy of the photon. We can also change the intensity of the light by making it a higher frequency. If we change that, if we make it a higher frequency, now that will change the kinetic energy of the photon in that case, because we can see the frequency is related to the kinetic energy. Right? But making the light brighter does not change the kinetic energy of the frequency. The only way we change the kinetic energy of the frequency, or the kinetic energy of the electron, is by changing the frequency of the light. That was our second surprising idea, that changing the frequency increases the kinetic energy. Another surprising point was that there's a minimum frequency required and no time delay within this material, no time delay between the photon arriving and the electron being emitted. Those were the surprising results of this experiment. Now, another important graph for the photoelectric effect is the current as a function of the stopping voltage graph. I'm just going to give myself another page here. If I graph the current, oops, let me change that, make that blue. Right, so if I graph the current in the circuit as a function of the voltage, and this is the voltage of the power source here, then we can see that when the power source is off, we are getting a current coming through the circuit. As these photons of light strike the metal plate, the electrons are released and a current goes through. That current will drop to zero when we arrive at the stopping voltage. And if we continue increasing the power source, then we're going to saturate the circuit and the current will eventually reach a maximum value. So this is our current as a function of the voltage graph. And what's important with this graph is to think about what happens when we change the metal or what happens when we change the frequency of the light. Right? So if we have the same frequency of light, but we change the brightness of the light, so a brighter light will not change the stopping voltage, but it will change the current in the circuit because a brighter light will increase the intensity of the circuit, will increase the number of photons arriving per second. So if I have a brighter light, but of the same frequency, then my current as a function of voltage graph will look the same in terms of the stopping voltage, but we'll have a higher current as a result because we've got more photons per second coming in if we have a brighter light. But those photons have the same frequency, and so the relationship between the energy and the frequency will remain the same. If I increase the frequency, then I'm going to move this graph one way or another. So for example, if I have the graph for, say, maybe this is the graph for, say, red light, or maybe blue light, because I'm using a blue pen. If I switch to red light, well, red has a lower energy in the frequency. It has a higher frequency, lower wavelength. No, pardon me, it has a longer wavelength, and so it has less energy, and so it's going to require less stopping voltage. So here's my red light. So as the wavelength gets longer, the energy carried by the photon gets smaller. The graph shifts to a smaller stopping voltage. So again, as we switch between different metals, different frequencies, then our graphs will change a little bit as a result. Now, do be careful with this, because when you think about intensity, the term intensity is used a lot in talking about this. And intensity is the power per unit area. So if you increase the intensity of the light, you can do that two ways. You can increase the intensity by increasing the brightness, in which case you've kept the frequency the same. You're just allowing more photons per second. So you can increase brightness, which is increasing the number of photons per second, or because intensity is related to power, and power is energy per second, we could also increase the energy of the photon, and that would also increase its intensity. So you could also increase the frequency of the photon, and that also will increase the intensity. And of course, if you increase the frequency, you're looking at this situation down here, where you've changed the frequency of the light. So if the question doesn't specifically state which one of these is increasing, you have to assume that both could increase. You can increase the intensity of the light by increasing the brightness or increasing the frequency. Both increase the amount of energy per second arriving at the metal plate. So just be a little aware of that. That's a little trick that pops up from time to time on these photoelectric effect questions. The questions say, oh, the intensity of the light is increased. Well, that means that the frequency of the light may be increased as well. So you have to be careful with that, because sometimes you tend to think, oh, if intensity is increased, it's just brighter. Well, that's not the whole story with intensity. So just be aware of that and just be careful of that, right? Another example of waves behaving like particles is this idea of Compton scattering. And again, this is a momentum relationship. And so it's like a collision. If you had a particle coming in and it struck a stationary particle, then you'd have a classical physics collision. One particle would end up traveling at some angle, the other particle would take off at the other angle, and you'd have a conservation of momentum occurring on each side. However, what if one of those is a photon of light? Here we have a photon of light coming in, so you wouldn't expect it to involve itself in a momentum collision like you would two particles, but in fact it does. This particle, this photon of light, collides with an electron, and then they both end up moving in different directions as a result. There's an exchange of energy and there's an exchange of momentum as a result of this collision between the photon and the electron. And so you can see the electron has gained energy and momentum as a result of the collision and heads off in a different angle. So the electron will gain kinetic energy as a result. That means that the photon has to have lost kinetic energy. Photon loses kinetic energy as a result of this collision. Now, for a photon, the energy is related to the wavelength. And so for a photon to lose kinetic energy, it doesn't slow down because photons travel at the speed of light. They are light waves. So how does it lose kinetic energy if it can't slow down? It loses and changes its wavelength, because the energy of a photon is given by hc over the wavelength. And so in this example of Compton scattering, what happens is the photon strikes the electron heads off with a kinetic energy, the photon heads off at a different angle, but it has also lost energy. That means its wavelength has actually increased. And that's where that energy change has occurred. It's changed the wavelength of that photon. So if it's coming in with an initial wavelength lambda 1, after it undergoes Compton scattering, it will have a slightly longer wavelength, lambda 2. There'll be a change in the wavelength of the photon as a result of this collision, because this collision is exchanging energy and momentum between the two particles. So we could write that change in wavelength as just lambda 2 minus lambda 1. That's the change in energy or change in wavelength of the photon as a result of the collision. And in the data booklet, you'll see the Compton scattering formula with this change in wavelength as a result. So this Compton scattering formula applies to this photon behaving like a particle and exchanging energy with the electron. And as a result, it has a change in wavelength. When we look at this Compton scattering formula, we can see that H, Planck's constant, me, mass of the electron, c, speed of light, and 1 minus cosine theta, where theta is the scattering angle for the photon. So the photon will be scattered through an angle theta, and so that shows up in our formula here. Right. Sometimes these types of question asks for the maximum scattering or the maximum change in wavelength. The maximum will occur when you have the biggest scattering angle. And the biggest scattering angle would be if the photon is scattered by 180 degrees. This will result in the largest wavelength change for the photon. That's our largest scattering angle you can have, is 180 degrees. And if you recall our trig, the cosine of 180 is -1. And so our Compton scattering formula, the change in wavelength, is just going to be 2h over the mass of the electron times the speed of light, because 1 minus minus 1 is 2. And so that will be our largest change in wavelength that will occur. And that'll happen if the photon hits dead on and bounces straight back. And then this electron will head off that way as a result. So that's another example of quantum physics where we have a wave behaving like a particle. And our final example, this is where we have a particle behaving like a wave. And this is an example of electron diffraction. So here we have a particle, the electron, which is undoubtedly a particle, is going to create an interference pattern as a result of passing through a crystal lattice. So the electron passes through the crystal lattice, and on the other side, an interference pattern is observed about where the electron ends up. So the electron passes through a crystal lattice and it diffracts as a result. So an interference pattern in where the electron position afterward ends up is seen. Well, interference patterns are classic wave-like effects, and you wouldn't expect this electron to create an interference pattern as it passes through this crystal lattice. You would expect just a random collection of electrons as it passes through, but it actually ends up with a very specific interference pattern as a result. And so a wave-like property, interference patterns, being demonstrated by a particle, the electron passing through. If we think about the atoms in a crystal, so if each of these dots represents an atom in a crystal, and here comes if we imagine two electrons coming in perfectly aligned with each other. This first electron is going to hit the crystal lattice, and then it's going to reflect. Off it goes. The second electron is also going to come in and hit the crystal lattice, and then it's also going to reflect, but it's going to reflect, it's going to hit that second layer of atoms in the crystal lattice. So you can see that when the first electron is here, the second electron is offset just by a little bit. And then when the first electron is bounced off, the second electron has to take this extra a little bit of time before it hits and is bounced off. So this puts the two electrons out of phase. So now there's a phase difference between the motion of these two electrons. Electron 1 hits right away and bounces off. Electron 2 takes this little extra bit of distance and time before it hits and bounces off. So on this side now, these electrons are slightly out of phase. Now, if they were particles, that wouldn't affect any of the observations. But if they were waves, this is the setup for a wave interference pattern. If that phase difference matches some multiple of the wavelength, then we're going to have an interference pattern that's going to develop as a result of the wave-like behavior. And in fact, this interference pattern has been observed and is used to measure incredibly small distances, like the distance between the atoms in this lattice. And so electron diffraction is an example of electrons showing interference patterns. They're behaving like waves. So we have particles behaving like waves in the electron diffraction. We have waves behaving like particles in the Compton effect, Compton scattering, and the photoelectric effect. And those are the key things about our quantum physics, right? There's also a little bit of quantum physics involved with the Bohr model, the quantization of angular momentum. And unfortunately, we won't have time to get into that today, but there's a little piece of the Bohr model, which is also higher level, which deserves a little review before you get to the exam as well. So I'm afraid that's our time. I wish I could go longer and keep talking about these atomic and nuclear properties and do more sample problems and get into it a little more detail, but I'm afraid that's our hour-and-a-half session. If you could please take a little time and complete our survey so that we can adjust our methods to suit your needs a little better, then happy to. Thank you very much for signing up and attending the session this morning. I hope everybody got a little something out of it. The recording will be available if you want to re-watch portions of it, if things happen too quickly and you want to revisit it, or if you want to take it piece by piece. And Gordon and I will hang out for another little while here and answer any of the questions you might have about the exam or about the topic or anything you want. So thank you very much for attending, and good luck on your November exams. I hope they go really well for everybody.